This is CS 402 for Thursday, June 5th, 2014. Whenever you're ready.
Yes, please have a picture-in-picture. All right. A reminder that warm-up 1 is due tonight at 11:45, and please look at the CLAP website to see the rules for late submission. Okay, and if you have code from previous semester, be careful not to copy from it, and best to get rid of it. And use the grading guideline. And yesterday I had people coming to the office hour. Still, some people are really not familiar with GDB. So make sure you got to get good at GDB. You're going to need it for warm-up number 2, and you're definitely going to need it for the kernel assignment. It's impossible to do the kernel assignment without using GDB. Okay, so this is the best time to to learn and learn Unix, install Ubuntu, etc. This lecture is an extra lecture to make up for the holiday last Monday, and it's meant as a continuation of yesterday's lecture. I'm going to assume that you have watched this extra lecture video before next Monday's lecture. Okay? Okay, so last time we were here talking about how the implementation of guarded commands in pthreads. And we're at this slide, and you can see that this slide has a lot of blue mark on it, and I usually use the blue, text to highlight, sort of important keywords. Okay, so let's go over this again. The condition variable is a queue of threads waiting for some kind of a notification. It's called event or condition. Okay, so you have a thread that's waiting for guard to become true, right? So we're implementing this. There. Okay, so we are trying to implement this. Okay, so you're going to have a thread trying to execute this code, and it needs to wait for the guard to become true. Okay, so if a thread that's waiting for the guard to become true, it would join this condition variable queue. Okay, they wait. So when they go into that queue, right? So there's a queue that they're waiting for this condition variable. Okay, they wait for the condition to be signaled. Okay, so in a way they're waiting for the right time to evaluate the guard again, okay? Because we don't really know exactly what the right time to evaluate the guard. The guard are changing all the time. So in order for this thread to evaluate the guard, the protocol over here is that it needs to join the queue to wait for the right time to evaluate the guard, okay? And then when it's okay to evaluate the guard, then it can go ahead and try to evaluate this expression. Okay, and from the last lecture, I said this guard can have a bunch of variable A, B, C, D. The guard can be A greater than 5, B less than 7, and C is greater than D, or something like that. All right, just an example. So one thread is going to do that, and the other thread that's going to make the guard to change value, for example, changing the variable A, B, or C, or D. Okay, so the thread that do something to potentially change the truth value of the guard, right? So why do I say potentially? Right over here, because if we want to say A is greater than 5, so if you change A from 3 to 4, well, that's not going to change the value of the guard. Okay, but you really don't want to write code to be that specific. So potentially that would change the guard. Then what you need to do is that you need to wake up the threads that were waiting in the queue to evaluate the guard. Okay, so this other thread that potentially can change the guard, they can signal or broadcast the condition. Okay, so the idea over here is that they will create that signal to say, hey, now this thread has been waiting in the condition variable queue, now it's time for it to evaluate the guard. Okay, or now it's time for that thread to have its turn to evaluate the guard. All right, so one thread is changing these variables A, B, C, D, and the other thread is waiting to evaluate the guard. Okay, so there's a timing difference between the time that this thread changed the variable ABCD. Maybe at the time it was changing the variable to, ABCD, the guard will become temporarily true for the other thread, but it is possible that once that's done, maybe another thread is going to come along and then change the guard again, so that, for the original thread that's waiting in the condition variable queue, the guard is becoming false. Okay, so the guard, again, continuously to change value from true to false. Okay, so there's no guarantee that the guard will be true when it's time for this other thread to evaluate the guard. Okay, so you have to sort of follow the protocol to make sure that, that all these interactions are done in just the right way. Okay, so conceptually, this event, you signal of the condition, right? So the event over here, okay, or the notification is done by signaling or broadcasting on that condition. And there's so signaling and broadcasting, there's only a minor difference. Signal meaning that you signal one thread to evaluate the guard, and broadcast meaning that a lot of threads is going to go and evaluate the guard. Okay, all right. So conceptually, this event will happen in an instant of time. So the duration of this event is, conceptually it's equal to 0. So if you have a thread that's interested in evaluating the guard, and if you don't wait for, you don't declare your interest in evaluating the guard, then when this event happens, you might miss it. Okay, so therefore, the protocol is that you have to get on the queue to wait for it in order for you to see it. If you're not on that queue, and if you try to evaluate the guard, then that's really the wrong procedure. Okay? So what you're supposed to do is, if you have a thread that's interested in evaluating the guard, you got to make sure you see the event. What you have to do is you have to call pthread condition wait. Okay? Pthread condition wait for has two arguments. One is that this condition is associated with the mutex. Okay? And the other one is the condition variable that we've been talking about. Okay? So what you have to do is that before you call this pthread condition wait, you have to make sure that you have this mutex locked by this thread. Okay, so you should only call pthread condition wait if you have the mutex locked. So when you call pthread condition wait, two things happen atomically, right? They're locked together so that no other thread can get in between. And the operations that are locked together are unblocking the mutex and wait for the event. Okay, so this thread has the mutex locked. When it calls pthread condition wait, it unlocks the mutex and wait for the event simultaneously. Okay, so why is it important for these things to be be locked together so that it's done atomically, right? If you have these two things, one is unlock the mutex, okay, and then you do the wait. If these two operations are not locked together, what happens is that, the condition can be signaled right between these two operations. Okay, if the condition is signaled right between these two operations, then this thread hasn't really got on the condition variable queue, so they will miss it. Okay, so if you make sure that these two operations are locked together, then there's no way for another thread to, be interleaved in the middle and then, signal the condition. All right, so it's very important to understand what is being atomically locked together. Okay, and also I'm using the word lock. Sometimes lock means mutex. Sometimes it just means lock. It's locking a bunch of operations together. Okay, so the word lock sometimes means that there's an implied lock somewhere there to make sure that these few operations are, tied together so that nothing can intervene. All right, so if you do it this way, when the event is signaled, the pthread condition wait will return with the mutex locked. Okay, so you lock the mutex before this function is called. You call pthread condition wait, okay, to wait for the condition, and eventually pthread condition wait is going to return. When it returns, it means that you have the mutex locked. Okay? So what it usually means, what it usually implies is that that particular condition has been signaled. Okay? This condition that you're waiting for has been signaled. But as it turns out that in the actual implementation of pthread, that's really not true. And we're going to get to that a little later. Okay? So right before this function is called, you lock the mutex. When you call this function, you get blocked waiting for the condition to be signaled. And when this function returns, you have the mutex locked again. Okay, so therefore you know that you are in the the synchronization box that we talked about, because if you're in the synchronization box, that means that you have the mutex locked. Okay, so therefore you have exclusive access to all these variables, and you can also execute critical section code. All right, so this is for the thread that need to wait for the condition. For the thread that need to signal the condition, it needs to call either pthread condition broadcast or pthread condition signal. And these guys only take one variable, the condition variable. Okay, so in this case, they don't need a mutex, but it's important that if you want to call pthread condition broadcast or a signal, you should have the associated mutex locked. Okay, so this way you won't be changing the guard at a bad time. Okay, so you should only call pthread condition broadcast or pthread condition signal if you have the corresponding mutex lock, and that's what you need to guarantee in your code. Okay, pthread is not going to force you to have some mutex lock, but you have to do it. Otherwise, you might end up signal the condition at the wrong time. Okay, and I guess we're going to see the difference. All right, so I'm going to go back to this picture again, showing the synchronization box, right? So the synchronization box is like the safe that I drew before. Only one thread is allowed to be inside this thread, and that's the thread, that has just held the lock, and we'll be able to open the thread, go in there, do something, and when it's done, you need to put the lock back. Put the key back. Okay, so in this picture, so I'm going to try to explain this picture. With respect to a mutex, right, this particular picture has a mutex, and this is the synchronization box for that mutex. So with respect to a mutex, a thread can be in one of the, in this case, one of 4 places now, because we have just introduced the condition variable. Okay, so the thread can be either waiting in the mutex queue, waiting to get into the synchronization box, or it could be inside the synchronization box. It got the lock, and it's running inside the the synchronization box. And pthread guarantee that if you use the mutex properly, only one thread can be inside the synchronization box at a time. Okay, so therefore, when you're inside the synchronization box, you can modify all these variables that are associated with the guard, A, B, C, D. You can execute critical section code, or the other thing that you can do is that you can go wait for a condition variable. In that case, this thread will get moved from inside the synchronization box to the condition variable queue. Okay, so therefore, that's another place where the thread can be. It can be waiting in the condition variable queue. Okay, I drew this picture so that the condition variable queue is outside of the synchronization box, right? Because when you are in the condition variable queue, you are not in the synchronization box. And there could be many threads that get queued up over here. Okay? And the other possible place for that thread is that, if it's not here, if it's not here, if it's not here, then it's outside somewhere doing something else. All right? So for a thread, it can only be in one of these 4 places. Okay? With respect to a mutex, in this picture, A, B, C are variables that can affect the value of the guard. Okay? So therefore, according to this picture, you're only allowed to access A, B, or C. Access meaning read or write. If you want to read it, you still need to get into the synchronization box. Okay? So you can access, this variable only if the thread is inside the synchronization box, which means that the thread needs to have its mutex locked. Okay? And how does the thread get into the synchronization box again? Right? It needs to either lock the mutex, okay? And when mutex lock return, you're in the synchronization box. And then if you decide to wait for a condition variable, you call pthread condition wait. And when pthread condition wait return, again, you are inside the synchronization box. Okay? So those are the 2 ways you can get inside of a synchronization box. All right, so when you signal a condition variable, okay, so this is another thread, right? Synchronizing the signaling condition variable. If you signal condition variable, all that happens is that you take the thread that's at the head of this queue, right? There's a thread sitting over here waiting for the condition to be signaled. This thread can move into the mutex queue. It doesn't go into the synchronization box right away, okay? Because there are other people waiting for the mutex to get into the synchronization box. So when you signal a condition variable, the only thing that happens is that the head of the condition variable queue, that thread, get moved into the mutex queue. Okay, and then that thread has to wait its turn to eventually make it to the head of the mutex queue, and next time, whoever that's in the synchronization box unlock the mutex, then that thread gets in. Okay, so it might take a long time between the time you signal the condition, when one thread signals the condition, until the other thread get into the synchronization box. Okay, and also remember that at the time when you signal the condition, that thread has to have the mutex lock in order for it to signal the condition. All right. So when you signal a condition, one thread get moved to the condition one thread get moved from the condition variable queue to the mutex queue. When you broadcast the condition variable, okay, in that case, all the threads in the condition variable queue get moved to the mutex queue. Everybody over here, they all join the mutex queue, and the condition variable queues become empty. All right, so that's the only difference between signal and broadcast. You need to, when you write your code, you need to determine, do you want to move everybody into the mutex queue, or you only want to move one thread into the queue? And that really depends on the semantics of your program. You can only add to the condition variable queues if you have the mutex lock, right? So to add yourself, so you're a thread, to add yourself to the condition variable queue, you need to call pthread condition wait. In that case, you have to make sure that you have the mutex locked. You can only modify the variable ABCD, the variable in the guard, if you have the mutex lock, right? So that, so again, this page tell you what the protocols that you have to follow. If you violate any of this code protocol, then your code might work sometime and sometime it might not work. Okay, so you have to follow every rule. You can only read variables in the guard. So basically the idea over here is that you are evaluating the guard where you read these variables. Even though you're not evaluating the guard, if you're just reading the variable, you have to have the mutex locked. Okay? You can only execute critical section code if you have the mutex locked, but that's, that's from previous lecture. All right? You have to follow all these rules. Okay, so putting all these things together, the way that you can implement the guard command is as follows, right? The guard commands, there are two types. One is with the guard, the other one is without the guard. So if you have a guard command, so you say when guard, you want to execute this command sequence, statement 1 through n. When you convert into pthread, you have to do it this way. So you're going to have a mutex associated with it. So we're going to assume that these two pieces of code, they're going to work together. So you're going to use a mutex, to guarantee that these threads work together. Okay? So you're going to call pthread mutex lock to lock the mutex, okay? Because you are not allowed to evaluate the guard without the mutex lock. Okay? Then you stay in this infinite loop right here. Okay? While not guard, right? So guard is a Boolean expression, evaluate equal to true or false. If it's equal to false, then not guard is going to be equal to true. Then, that means the guard is not true. So therefore, what you're supposed to do is to wait for the condition. So you call pthread condition wait to get on the condition variable queue. And when you call this function, it atomically unlock the mutex and puts this thread on the condition variable queue. Okay? When this function returns, that means that somebody has signaled the condition, this thread moves all the way back into the mutex queue, made all the way to the beginning of the mutex queue, and then get into the synchronization box, and that's when this guy returned. Okay? When this guy returned, is the guard true? Well, you don't know, but you have the lock, right? So therefore, what you're going to do is that, this is an infinite loop, so you go back over here, and you evaluate the guard again. Okay, so you only evaluate the guard when you have the mutex lock. So again, you evaluate the guard. If guard equal to false, then you wait for the condition to be signaled again. So you keep staying in this loop until eventually you have the mutex lock and the guard becomes true. Okay, so at this point, you know that that you see the guard is true. Okay, and then you jump out of the while loop and then you execute statement 1 all the way through n. Okay, and then when you're done over here, you unlock the mutex. All right, so now we can think about going back to the last lecture, right? We said the semantics of the guard command used in this way is that evaluating the guard when the guard is true and execute all these command sequence is an atomic operation. All right, is that true in this case? Okay, when you evaluate the guard to be true, you execute all these statements, and then you have the mutex lock, so all that operations are done in an atomic way because there is no other thread that is supposed to interfere with you. Okay, so therefore, I can claim that this is the implementation of the guard command. All right, so this might not be obvious, so look at this a few times and convince yourself that this actually works. Okay, the second piece of code is there's no guard, right? So in this case, in this code, you might modify the guard. So what you're supposed to do is that you should lock the mutex, the same mutex as the one that's being used over here, modify, the guard. Okay, so over here means that you can change the variable associated with the guard. And then when the variables is changed, well, this guy doesn't really know exactly what the guard looks like. Okay, all it knows is that the variable that you modify over here might affect the evaluation of the guard. So therefore, what you do is that you broadcast the condition or you signal the condition, depending on the semantics of your code. Okay, so over here you can actually if the other thread always uses this particular code to reevaluate the guard, then all you have to do is to broadcast the condition. Okay, because if there are 20 threads waiting in the condition variable queue, they all get a chance to evaluate the guard, and maybe only one of them will go through. The other 19 will get back into the condition variable queue. Okay, so you can always do a broadcast if the code is done properly. but in a way it's kind of a waste because all those 19 threads, if there's no, when you move those 20 threads from the condition variable queue to the mutex queue, if you know for sure only one of them will get in, it will actually get to execute critical section code, then you should only let one of them go. There's really no need for 20 of them to go, and then 19 of them is going to come right back into the condition variable queue. Okay, so over here, this is their sort of efficiency consideration where you need to choose between pthread condition broadcast and pthread condition signal. All right, but the important message over here is that you change the guard, you signal or broadcast the condition, and then you unlock the mutex. All right, so again, you're following the rule that when you modify the variable A, B, C, D, you always have the mutex locked. All right, and again, this claim is that this code implement this guarded command. All right, so condition variable, just like mutex, need to be evaluated. If you have if you allocate the condition variable in the heap, then you need to call init, and when you're done with it, you need to call destroy. Otherwise, you can just use it, this way. All right. And usually the condition variable attributes, just like the mutex attributes, are not used. All right, so we're going to see how to use, this guarded command in a more elaborate, case. So in this case, we're going to look at something called the readers and writers. There's a piece of shared data that's being shared by a bunch of threads. Okay, so over here we have 100 readers and 1 writers. Okay, so one shared piece of data. All the other, threads, they all want to read it. There's only one guy that are modifying it. Right, so you can think about this like a database operation. Database, example that you have a database, right? So this is your database. Okay, you only change it once in a while. Most of the time, you are just making queries to read from the database. Okay, so you have tons of threads that are reading from the database, and once in a while, somebody will update the database. Okay, so what should be the right semantics over here, right? When you are reading all the data, you can do this in parallel, right? All 100 threads can actually go at it, in parallel. There's no problem, right? As long as the data doesn't change. Okay, but when you want to change the data, what do you have to do? When you're changing the data, you got to make sure that all the readers are gone. Right? There's nobody reading the database. Then at that point, you lock the database and you write to it. All right? So again, if you use a single mutex to do the whole thing, it's an overkill. Okay? If we use the guarded command, we can actually do this properly. All right? So when you are writing to the data, you got to make sure that there's no reader. And when you are reading the data, you got to make sure there's no writers that are writing to it, but you can have other readers that are reading in parallel. Okay, so therefore, if you write the code is going to look like this. Okay, I have a reader, so I have threads, the reader and the writer. Right, the reader, you can have 100 instances of threads calling the reader function. And you can have multiple writers that are calling this thing, and the writers will have to get into a queue. Okay, but the readers can do things in parallel. Okay, so the reader code says when the writer is equal to 0, when the number of writers, right? Again, this is a guarded command, right? When the guard is when there's no writer, okay, I'm going to increment the reader, okay, and then I'm going to call the read function to actually start, making database query and, read the data. And this can be a very, very slow operation. Okay, so again, if you go back to the implementation of the guarded command, the mutex is locked right here at the beginning, and then it's unlocked in the end. So this read operation is actually done without the mutex having locked. Okay, so this is why what we talk about, the reason we need all this kind of stuff is to increase the amount of parallelism without using a coarse-grained, mutex that just lock the entire thing together. Okay, we're going to use the mutex sort of in an intelligent way, and in this case, we're going to use the mutex together with a condition variable to implement the guarded command. All right, so over here, for one reader, right, one reader wants to read, it will call this function, okay? So when the number of writers is equal to 0, reader is going to get incremented, and you can go ahead and read, okay? And when you're finished reading for this thread, it's going to decrement the number of readers using the guarded command. Okay, so again, this, this is 3 machine instructions, so you have to do it, using a, guarded command to make sure it's done in an atomic way. All right, what about the writers? The writer has to wait to make sure that there's no reader that are active, and also there's no writers that are active. Okay, so over here, we're going to say that, the writers is going to call this function. You can also have multiple writers calling this function. Okay, so when one writer comes in over here, it will check the guard. The guard means that if there's no writer and there's no reader, So that means that nobody is actively looking at the data or modifying the data. Then this writer is allowed to get in. Okay, so over here, it just increment the number of writers. So the writers initially is going to be equal to 0, and now you're going to change it to 1. Okay, and you change it to 1 in a protected way, right? Because now this writers is part of the guard over here, is part of the guard over here. So you can only change it when you are in the synchronization box. Okay, you increment the writer, and then you get out of the, you get out of this guard command, and then at that point you can actually do the write. Okay, so this is modifying a database, so that can take a long time for this to finish, and you are modifying a database without having the mutex locked. Okay, so at this time, more readers can come in, and they're all going to see writers not equal to 0, so they all have to wait. Okay, the writer is going to take his time modifying the database. When it's done, it's going to call this guard command to decrement the writers back to 0. Okay, at this point, when this guy goes to 0, then what happens is that the reader can actually come in and read. Also, another writer, if there's another writer waiting, then that guy can start. Okay, so either one is going to win, but not both of them is going to win. All right, so the textbook show you this code. They also show you some kind of sanity check by adding assertions in them. But if you really understand the code, the assertions are always going to be true, so they're really not necessary. Okay, so over here, what we need to notice is that, the variable over here, readers, right, you're changing the variable reader. So this is the variable ABC that I talk about. You need to look at what guard does this variable belong to, because those are the, so by looking at what guard belong to, then you know which condition variable you have to signal. Okay, so therefore readers, when you decrement the readers over here, readers can eventually, might become 0. Okay, so it will not affect this guard, right, because this guard does not involve the reader. Okay, so this is kind of a weird situation. We're actually going to have two different guards. One only involve writers, and the other one involves writers and readers. Okay, so if you look at the readers variable, this is the variable that you're changing, so it's only going to affect this particular guard. So therefore, after you modify readers, you're supposed to signal the condition, but you're going to signal the condition associated with this guard. Okay, so what I'm saying right now is that there are actually going to be two different condition variables. One is for this guard, and the other one is for this guard. Okay, so potentially, one mutex can work with multiple condition variables. Okay, because every condition variable might be associated with a guard. All right, so I'm using the word might be. Again, you have to look at your code to see what makes sense. Okay, but you have to follow the protocol, and then you're going to try to write your code so that it's a little more efficient. All right, what about the writers over here? Okay, over here, when you modify the writers, you notice that this writer appears here and the writers appear here. So in this case, after you modify the writers, you might have to signal condition variables for both condition, one for this guard and one for this guard. All right, so writing this in the guarded command, okay, you can see that this works, but when you convert this code into P threads, then you have more work to do because you have to decide which condition variables you have to signal. All right? Over here, what about when you increment the readers over here? Okay, do you have to signal any condition? All right, so in this case, it is possible that, you might want to, because over here you change the guard, right? Anytime you change a variable that's being used by some guard, maybe you need to signal some condition. But if you examine all the guard over here, you will see that in this case, you actually don't have to worry about it. Okay, because over here I increment the guard. All these other places, when I check the guard, I always check whether the reader is equal to 0 or not. Okay, or the writer is equal to 0 or not. So when you're incrementing a reader that can never be negative, you never have to worry about whether it's being 0 or not. Okay, so therefore in this case, when you change the reader over here, you don't have to signal a condition. Okay, similarly, when you over here, you increment the number of writers over here, this one is checking the writers equal to 0, you also don't have to, signal any condition. All right? Okay, so this picture actually changed a little bit, right? We're going to have the readers and writer thread. We have a single mutex that we're implementing. In this case, we're going to end up with two condition variables. One is associated with the writers, and the other one is associated with the reader. Okay? we can actually use a single condition variable. Okay, so anybody who wants to wait to evaluate a guard, in this case, anything that's related to writers or reader, you can use it using one condition variable, so have them wait on that queue. And anytime you change readers or writer, you can wake it up. And if they implement these kind of stuff correctly, then you don't have to worry about you don't have to worry about them doing the wrong things, because they will always do the right things. Okay, they will only evaluate the guard when they have the mutex lock, so it's really not a problem. Okay, so you can use one condition variable, but in this case, it's better to use two, because you're going to end up with more parallelism when you run these two programs. Okay, so to be more efficient, you can use multiple condition variables, so you don't have to wake up a thread unnecessarily. Okay, so we're going to use one condition variable for the reader's guard and one condition variable for the writer's guard, since the expressions are different. Okay, if the guard is exactly the same for one thread versus the other, well, then then all you have to do is use one condition variable, and then when you change the variable, you can signal the condition or broadcast the condition. All right, so we're going to convert that code into p threads, right? So now it becomes, right, the reader is going to call. Right, over here is the guard, while the, I guess the guard command, right, is when the guard is true, execute the command sequence, right? And the way you implement this is this code, okay? So this code is going to implement this right here, okay? When writers equal to 0, increment the readers, okay? So over here, you lock the mutex, while not guard, right, not guard, this is guard exactly as the previous slide, while not guard, p thread condition wait, and this one, the condition you're going to wait for is the reader's queue, okay? And then eventually when this guard becomes true and you have the mutex lock, you come increment the reader, and then you unlock the mutex, okay? Now you can go ahead and read, all right? And then when you are ready to, when you're finished reading, you lock the mutex, you decrement the readers, you check if the reader is equal to 0 or not. If it's equal to 0, then you signal the condition, okay? And then this condition variable u is the one associated with the writers, because at this point you might want to wake up the writers so the writer can see if there's no readers, that are actively reading the database. Okay, so over here you only check it when the number of readers equal to 0. Okay, when the number of readers after you decrement it is not equal to 0, you shouldn't really bother to wake up, the writer thread, because there's no way for it to see that, to see the number of readers equal to 0. Okay, and also in this particular case, you only have these two, two pieces of code that are dealing with the reader and writer, queue. So therefore, you don't really have to wake up the writer. If you have other code that also might decrement the reader, well, then you might have to wake up, the writer. Anyways, you have to do your analysis to determine exactly when you wake up the writers so that you can be more efficient. And then finally, you unlock the mutex, right? Again, the bottom part of this code implement, this guy right here. All right? Similarly, if you look at the writers over here, the top part implement the top part of the writer. It locks the mutex while not, this is the guard, right? While not guard, okay, go p thread condition wait. Eventually, when the guard is true, you have the mutex lock. You come here, you increment the writers, and then you unlock the mutex. So when you're doing the write, you don't have the mutex lock, okay? And then when you're done, you lock the mutex, you decrement the writers. But in this case, you're gonna potentially affect two guards, right? So therefore, you're gonna call p thread conditional signal on the writer's queue and then also on the reader's queue. Okay. In this case, I know that I can only have one writers at a time, right? So the writers, this variable only go from 0 or 1, so I don't have to check whether it's equal to 0 or not because I know it's equal to 0. Okay. Then I signal the condition because I can only have one writers at a time. So why do a broadcast if there are multiple writers waiting in the queue, right? Because only one can get it. Okay, so therefore I'm doing the signal. What about the reader's queue? The reader's queue might have 100 thread waiting in that condition variable and want all of them to start reading. Okay, so therefore instead of calling signal, I should call broadcast because I want all of them to start reading. If you only call signal right now, only one of them will start reading. So who's going to wake up all the other readers' thread? Okay? Well, as it turns out, nobody's going to do that. So therefore, your program might get stuck. Okay? So therefore, it's very important in our scenario when you have multiple readers and a single and multiple writers over here, you broadcast the condition. All right, and then you unlock the mutex, and the bottom part implement the bottom part of the previous slide. All right. Okay, again, read this code, carefully. Okay, so what is the problem with this code? Okay, the code operationally is correct, okay, but it's going to have something called a starvation problem. Okay, this starvation problem only happens when you always have readers. Okay, you have a very busy database, you're reading it all the time, right? For example, you have a popular website, people are using it all the time, people are just reading your database. So is it possible for the writer never gets in? Okay, so it is possible, right? If you have 100 readers over here, they're all executing over here. A writer comes wanting to write. As reader leaves, more reader can come in. Okay, so therefore, this guy never gets to execute. Okay, so in a way, the readers basically never gets to 0. Okay, so in that case, the writer will starve this guy. So this is not called a deadlock. This is actually called a live lock. Okay, where the writers will, basically never get to execute, and there's no deadlock. Okay, so the solution over here, right? So why do you end up having this particular problem? Well, you can say that, well, it's because the readers has higher priority than the writers. Okay, but I really haven't done any pthread code to enable priority. So why is that? The reader has higher priority. Well, it's because the way the code is written over here, right? Over here it says the writer will not get in, okay, as long as the number of readers is not equal to 0. Okay, so if you have readers keep coming in, then the writer never gets a chance to run. Okay, so the solution is to reverse the priority. Okay, is to have the writers has a little higher priority, but again, you don't want to mess around with the thread priority. You can do it simply with this solution. Okay, this solution basically introduces an extra variable, and you call it active writers. Okay, so as long as there are writers waiting in the condition variable queues for the writer, then you also want to block the readers. Okay, so in this case, what you can do is that over here, you change the definition of writers. The writer is no longer the number of active writers. This is writer over here is that as long as any writers that are interested in writing, then the reader, the reader doesn't get in. Okay, so once you have one writers coming into wait for to wait to write. Right? Again, here's the database. Okay, and writers coming over here, the readers try to read it. Right, you have many readers over here. Okay, as long as one guy start waiting to write a database, then all the readers, if they are currently reading, they can continue to read, but they will all eventually have to finish. Okay, you are not allowing the readers to come in anymore. Okay, because all the new readers will block right over here because there are writers that are waiting to write. Okay, so the writers become writers waiting to write, and then you can only decrement the reader at that point, and eventually the number of readers is going to become 0, and then the writer will get it. Okay, so this gives the reader a higher priority. If there's a reader, so it's not a preemptive priority, right? When the readers need, you give the writer a higher priority. It's not a preemptive priority because when you need to write, you still have to wait for all the readers to clear out before you write. Okay, so you get on this queue, and then as soon as you get on this queue, all the readers have to get out. New reader will have to wait for you because you have higher priority over them. Okay, so this is the way to do a priority without actually, setting the priority on the threads. All right, so please read this code carefully and make sure you understand why this guy actually works. Okay, so now the writer has higher priority. You're going to get starvation problem. Well, you're going to get starvation problem if you always have writers and you have less readers. Okay, but in a real life situation, if you look at an application, okay, the number of writers versus the number of reader, well, hopefully the number of readers is going to be a lot more than the number of writers. You only modify the database once in a while, so therefore it's okay to do that. All right? So again, you need to do the analysis based on your understanding of the application and decide exactly which way are you supposed to write your code. Okay, so to improve reader, so we'll change the code a little bit. Okay, turns out this code is exactly the same because, if you look at the guarded command, okay, the guarded command, this is exactly the same code as before. Over here is slightly different, okay, but the interpretation of the writers is different, but the code is still staying the same. Okay, the improved writer. And this one is just a straightforward conversion from the previous guarded command code, again, into pthreads. All right, so if you look at the guarded command, that's like pseudocode. If you're convinced that that code is correct, then the conversion is fairly straightforward. The only thing you have to figure out is that, in the end, what condition to signal. All right? Okay, so the reader-writer is very popular. So it turns out that POSIX even implement readers and writer. Okay, so there's a bunch of functions over here. For warm-up number 2, I'm going to suggest you to stick to the basics and just use the mutex and the condition variable and don't use anything else. Okay, even this, there are places this might be appropriate. Okay, so this way you really understand the basic, and then you can use the basic stuff to implement anything else. Right, so try not to use this for warm-up number 2. The last synchronization we're going to talk about is called barrier synchronization. So the idea over here is that this is used in kind of a, you can call it in a fork join network. You have a thread that's going to do something, okay, but now they realize that there are a bunch of stuff they can do in parallel. So what it will do is that it will fork off a bunch of threads, okay. So in this example, I'm going to fork off 4 child threads, okay. So these are the worker thread. They're going to perform the work in parallel. But eventually, when these guys are finished, okay, then, so when these 4 threads are finished, then I want this thread to continue. Okay? So in a way, this thread is going to wait for these 4 threads to finish before this guy continues. Okay? So this is called barrier synchronization, because what happens is that you set a barrier over here, the barrier wait for all 5 threads to be done with what they're doing before proceeding. Okay, so one thing that you can do is that you can actually dynamically create these 4 threads using pthread create, and then over here you just join with those 4 threads. So that's a simple way to do barrier synchronization. Okay, but we want to do something a little different. We want to make use sort of a thread pool kind of a way of organizing our thread. We're going to create a bunch of threads, and we're going to have these threads to do work for us without destroying them. Okay, so in that case, when we reach this synchronization point, we're gonna call up these worker threads. They're already sitting around doing nothing. We're gonna ask them to do these 4 tasks, and when they are done, we're gonna synchronize all these 5 threads, and then these 4 threads can go to sleep, and then my main thread will continue to move forward. Okay, so in a way, I can draw this picture like the main thread is coming over here, create these 4 threads, and then it will wait at the barrier for all these 5 threads to join together without actually killing the threads, okay, and then it can move forward. All right, so how do you implement this? Okay, so this is one way to implement it, right? You call this barrier sync, okay? So when all the threads, all these 5 threads are ready to synchronize, they will call barrier sync, and the barrier sync over here knows how many threads it needs to wait for. Okay, so in this case, we're going to use the number n to denote how many threads you have to wait for. So n is equal to 5 in this example. Okay, so the first thread, after it creates those 4 child threads, it's going to call barrier sync, and it's going to come over here. Count is initially equal to 0. So this thread is going to increment the count, and the count is going to be less than 5. So therefore, in that case, what it will do is that it will call pthread condition wait. Okay, so the idea over here is that all these, so the first 4 threads that are coming to the barrier, they all wait in the condition variable queue, and the 5th thread, the last one comes in, they will do a condition broadcast, and all of them can leave the barrier. Okay, so when all of them eventually unblock, they will, return from the barrier synchronization, so they all left the, the barrier, sort of at the same time. All right, so as long as you are not the last thread, you call pthread condition wait, right? So over here, this is the mutex queue, okay? And this is the synchronization box, right? Here's the condition variable queue. So the first 4 threads, they're all waiting right here. The 5th thread come over here. Count is not less than n, it's equal to n. So therefore it comes over here. It sets count equal to 0 and do a condition broadcast, make everybody go back into the mutex queue. And then the next time when they will return from pthread condition wait, and they will unlock the mutex and they will get out. Okay? So this code is supposed to work. As it turns out that, because the way pthreads is implemented, it doesn't really quite work. Okay? And the problem is that pthread condition wait can actually return spontaneously. Okay? Meaning that it will actually return when the signal, when the condition hasn't even been signaled. Okay? So why pthread just don't fix the bugs? If they can fix the bugs, then this code can be used. Okay, as it turns out that pthread people insist that this must be allowed, okay, that this particular function, is allowed to return spontaneously without, seeing the signal. Okay, so, and the reason is that because, we're going to talk about in the next set of slides, is that there's these things called Unix signals, and the signals can actually cause one of these functions to return, and when it returns, it doesn't really remember whether the condition has been signaled or not. Okay, so therefore, the way that you're supposed to use condition signal is that you are required to use pthread condition in that infinite loop. You have to say, while not guard, pthread condition signal. You should never use pthread condition signal all by itself. Okay, because in this code, there's no while loop, so this is the wrong way to use pthread condition signal. Okay, you have to accept the fact that pthread condition wait can just return spontaneously, and pthread people is not going to implement this in a different way. All right. So the solution over here, right, is that you put this pthread condition wait inside this while loop, right, while not guard pthread condition wait. Okay, as it turns out, this code also doesn't work because what happens is that if you have this guard over here checking whether count is less than n or not, then when the last thread signal the condition, these threads, they might all see that the count equal to 0, so they all continue to wait for the condition. Okay, so therefore, only the last thread will leave the barrier. All the other guys, they might get stuck at the barrier. Okay, so this is really not a solution. And the real solution is to realize that, well, the problem over here with this code is that you put count inside this, inside the guard, and also you want to change stuff over here, and there's really no, there's really no simple logic that you can implement to make this work. Okay, so the real solution is to not put the count inside this guard. Okay, if you don't put the guard, the count inside the guard, there's actually for this thing to work. Okay, the idea over here is to create the idea of generation. So again, let's draw this picture. You have one thread fork off 4 threads, and then they're going to join over here. This guy's going to come here to do the synchronization. Okay, we can call this one generation. Okay, so when this thread eventually finishes, go to the next time, eventually it might come here and do the same thing over again. That will be the next generation. Okay, so what happens is that when one generation is finished, then we're going to say, well, all the current threads that are waiting at the barrier, they can all leave. Okay, and now we are going to the new generation. So next time any thread that comes in, they will belong to the new generation. Okay, so if we use a generation over here, I guess I don't have a declaration of generation. Over here, just in generation equal to 0. Okay, so over here, when you're in this particular code, if you are not the last thread, you remember which generation you belong to, and then you stay in this infinite loop, okay, waiting for the generation number to get incremented. Okay, and the generation is only incremented if you are the last thread that comes into the barrier synchronization. Okay, so the last thread over here will come in over here, increment the generation, and then it can broadcast the condition, release all these threads that are waiting, all the n-1 thread that are waiting for the condition variable to be signaled, and they will all come here and realize that the generation now has been incremented, which means that the last guy has come to the barrier. Okay, so therefore all these threads will jump out, and they will all unlock the mutex, they will all leave the barrier all at the same time. All right, and then the barrier synchronization. So again, look at this code and convince yourself that this is actually the correct implementation. All right, barrier synchronization is a very, it's used very often. So POSIX, again, implement, these functions. And again, if you want to do that in warm-up 2, I suggest you, again, go through the basics and not use this approach. All right, so we're done with this. We're going to look at the second part of threading. Let's see. Okay, so we're finished with thread synchronization. We're going to go to the next part, which look at safety. Okay, so we're going to look at, so this set of slides contains 2 things. One is look at thread safety, and the other part is called deviation. Okay, so deviation is that, you have a thread so a thread is a thread of execution. What if you want a thread to deviate from its normal thread of execution? For example, you want to kill it, or you want to have it do something else, so that belongs to deviation. Okay, the first thing we're going to look at is the concept of thread safety. All right, so what is thread safety? Unix was developed way before thread was commonly used, right? So in the good old days, one process, there's really no concept of thread. So you're executing a process because the process only consists of one thread of execution. Okay? So at that point, the Unix library, so Unix has, system call library, they have C libraries, a bunch of libraries. They were built without the threads in mind. Okay? So running code using these libraries, when later on when threads become popular, this library becomes not safe. Okay? So to make these libraries safe to run under multi-threading, that's known as thread safety. Okay? So thread safety basically means that you want to write some library code, and you want to make sure these library codes are meant to be called by other applications. Okay? So you want to make your library code safe under multi-threading environment. Okay? So that is thread safety. We're going to look at some of the, so it turns out that different kind of problem have different kind of solution. We're going to look at some examples, in this set of slides. All right, so one is regarding global variables. Okay, so we already see, so what kind of global variables? When you make a system call, the system calls are implemented in the system call library. I think it's part of the C library. Okay. When you make the write call, when write fails, it's going to set error number into a particular value. Okay. Now it's going to be a problem when you have multi-threaded environment, right? Because you can have multiple threads. Both of, let's say you have two threads. Both of them are calling write. Both of them failed. Now error number is a global variable. So when you try to read it, it might be possible that you have one thread reading the error number from another thread. Okay, because it's a shared global variable, so that doesn't really work. Okay, so this particular problem, right? You only have one single global variable error number, ERRNO, right? It's a global variable, right? It's a global variable, so this variable lives in the data segment. You have two threads, both of them want to change it. Well, then you're going to end up with a problem. Okay, so therefore, in this particular case, the terminology that people will use is that this library implementation of write, if you have this problem, then the write is not re-entrant. Okay, so or it's not thread safe. Okay, they both mean the same thing. Okay, so when you have multiple threads that are running using this library function, then things are not going to work properly. Okay, and in this example, the reason they're not working properly because they share a global variable. Okay. So what is the solution for this? Okay, in order for you to fix, so this problem is kind of happen with all the system calls. Okay, every system call, when it returns an error, it needs to set the global variable error number. So none of the system call is going to be thread safe. Okay, so the solution is that you don't want to build a new operating system. Okay, so you want to have a solution that's backwards compatible. Okay, so all the old program that used to work in a non-thread safe environment, maybe all you have to do is recompile them, and now they can be used under multi-threaded environment. Okay, so that would be the ideal situation, right? You only have to recompile the old code. You don't have to rewrite the code because they're all working before. Okay, so all you need to do is to make sure that error number, when you make a call like this, okay, what does it mean when you make a call like this, right? Okay, you're trying to associate the error number with this particular write. Okay, so how do you associate an error number with this particular write? Well, you say, well, there's one thread that's making this function call. So actually, I'm gonna, this particular write was done on behalf of this thread. Okay, so what you really want to say is that this error number belongs to this thread. Okay, when write fails, I want to modify the error number associated with this thread. Okay, if you have another thread that calls the same function, then when write fails, the error number that it's going to set is going to be associated with that thread. Okay, so basically what you're saying is that there need to be one error number per thread. Okay, so how do you implement that? Okay, so the idea over here is that, one good place to store something that are specific to a thread is the thread control block. Okay, people who are implementing the system call, what you will do is that, inside the thread control block, you can allocate something called thread-specific data. Okay, so inside the data structure, you're going to have an array of thread-specific data, and one of them is an error number. Okay, so this way, when one thread is calling the write system call, and the write system call is going to modify error number, well, you will end up modifying this error number. Okay, for another thread, so this is TCB1, TCB2, For another thread, if that thread call write and that thread fails, it will modify error number in that thread control block in the thread specific data in the thread control block for that thread. Okay, so in this case, the error number is no longer a global variable, right? So the error number is actually referring to a specific location inside the thread specific data of a thread control block. Okay, so the solution turned out to be very simple. Inside the header file for defining error number, right? So when you're using error number, you're supposed to do pound include errno.h. Okay, so inside that, it used to say, error number is a global variable. Now it changed into a function call. Okay, so this particular function call, if you give it a thread ID, this function will retrieve the error number inside this area. Okay, so therefore you can say error number equal to this. You can actually set this particular location to a different value. And if you want to read the error number, it will actually fetch this memory location. All right, so with this solution, it actually is a very nice solution. You don't have to change all the code that you have written. All you do is to redefine the header file, okay, and now you do a recompile, and then, everything will work. Okay, so this is really the ideal situation to make a code thread safe. All right, so not everything works that way. Here's another example of another C library call, get host by name. Okay, I think this is a C library call or a networking library call because this is related to networking. I think the generic term for that is the sockets library. Okay, the socket library is related to networking. Okay, so inside there, there's this function, get host by name. And so if you're given a host name, it will return to you a data structure that contains information about this host name. Okay, so for example, if you call get host by name and you give it nunkey.usc.edu, it's going to return you with a data structure that says the nunkey.usc.edu actually has several IP addresses. And here are all the list of the IP addresses. Okay, so the trouble with this library call or a system call is that this one actually returned to you a structure, and this structure is not part of the argument. Okay, so if you think about where is this data structure lies. Okay, it turns out that this one, again, it's in the data segment of your program. So when you, create your executable, there's actually a private area in that data segment that will store this result. Okay, so of course, this problem is that if you have multiple threads, both threads are calling this, they're going to wipe out each other in the data segment. Okay, so therefore, this code is not re-entrant. Okay. The positive solution to this particular problem is to create a re-entrant version of this function. Okay, so in that case, if you have a program that's going to be thread safe because you're using multi-threading, the idea over here is that, well, you must have, that piece of code, now you're going to use multi-threading with it. You must change your code inside there. Okay, if you're changing that code, then you can also change this particular function call. Okay, so the problem with the error number is that those are just system calls, so therefore you're really not writing any code to do multi-threading, but now with a simple recompile, everything will work. This one actually requires to do a little work. For those kind of code, you actually have to call a different get host by name, and this one is called get host by name _r. This is the re-entrant version of get host by name. If you call this function, you will be thread safe. Okay, and the reason you'll be thread safe is that you're providing a data structure to store the result. Okay, so this one, you can see that the name is the same thing as this one, but then you provide a bunch of stuff to hold the return value. All right, so in this case, so this is not as ideal as the previous solution because you actually have to make a different, different call. Okay, but either way, this is what you have to do to make your code thread safe. There are also cases when you have doing printf. Okay, so what's wrong with printf, right? Printf, both of the, so let's say that you have printf, both of them either they're printing to a file or they are printing to the terminal. So in this case, they're all printing to standard out, right? They're using printf. Printf print to standard out. You have one thread executing this and the other thread executing this in parallel. It is possible when you're calling printf, printf try to print to a device. Okay, so therefore, when you try to print to a device, you might get interrupted. You might, your thread might get swapped out, or anything can happen. So it is possible you will print a few things. Okay, you will print the first 5 character, and then you get switched to, do something else. Okay? And then the other guy will come in and print, the first 4 character. You're going to end up, with, the phrase "go to hell" over here. All right. So anyway, you might end up printing a message that's not desirable. Okay? You're going to run into this in warm-up number 2. You're going to have 3 threads running, and they all try to print the trace. Your simulation, you're doing a simulation, and then you need to print out a trace of your simulation. So they're all competing for the terminal. So you got to make sure that they don't step on each other's toe. Okay? So in this case, what you can do is that you can actually, one simple thing to do is that you can use a mutex. Okay? You can use a mutex when you need to print to standard output. You lock the mutex, do a print, and you unlock the mutex. Then, oops, where did it go? Okay, so in that case, what happened is that you will add pthread mutex lock right here, pthread mutex unlock right here, and pthread mutex lock, pthread mutex unlock. This way, you're not going to get interference from another thread. Okay? There's another way to go, very similar. If you're using, the data type file star, if you're, using fgets, fprintf, and stuff like that, you can actually lock the standard out. So you can say flock file. Over here, you can provide, you just type std out. Okay? And then you can unlock the file after you finish printing. Okay? So this way, you can also make sure that they don't get into each other's way. All right? So it's very similar to using a mutex. All right. Okay. Other things to make sure that things are thread safe when you have multiple threads is that if you are waiting for a condition variable to become true, over here it sort of tells you that if you get tired of waiting something, like you get into a supermarket line and then you waited too long, so you basically drop all your grocery and you leave. Not very nice, but sometimes people do that. When you are sleeping, normally, suspend your thread for a certain amount of time. There are these functions called, sleep or nanosleep or usleep, right? Something called usleep, S-L-E-E-P. Usleep, sleep for a certain number of microseconds. Nanosleep, sleep number of seconds and, nanosecond, etc. So what happens is that when this function is called, in this example, it will sleep for 3 seconds plus 1,000 nanoseconds, so 3 seconds plus 1 microsecond, okay? And then this function will suspend your thread for that amount of time, and then will return. One important thing to understand in your warm-up 2 is that, Unix and Linux, these are best effort operating systems. So when you try to sleep for 3 seconds and 1 nanosecond, this function will return, at least 3 seconds and 1 microsecond later, but it will return 4 seconds later. Okay? What happens is that if you have a machine that's too busy, your machine is doing something else, so when this guy returns, there's no guarantee it's going to be exactly 3 seconds plus 1 microseconds. It might be longer. Okay? So the Unix will try their best to accommodate what you ask for, but usually it doesn't really end up doing exactly that. Okay? Even if you have an exclusive machine, your machine might be running 50 different processes. So therefore, when this thread is ready to run, well, maybe something else is using the CPU. Okay? So this is not very precise. All right. So this is one way to call one thing that you can do to suspend your thread for a certain amount of time. Okay? The other case that you can do is that if you're waiting for a condition variable, you're waiting for a mutex, or you're waiting for a condition to be signaled, and then you're tired of waiting. In that case, instead of calling pthread condition wait, you can call pthread condition timed wait. Okay, so this one is an extra argument. This extra argument says, when do you want to give up? Okay, so over here, this is, these two calls are different because this one tells you how many more seconds and milliseconds to wait. This one actually specifies an absolute time for you to give up, to give up waiting. Okay? So you got to be careful when you do something like that. You got to figure out what the current time is, and then you got to figure out, how much you want to wait, and then you figure out when is the time you want to give up. Okay? So here's some code. I'm not going to get into any detail, but the important thing over here is that you can call pthread condition wait. Okay, and there's some code that's missing over here. It doesn't really fit. You need to change the return code of pthread condition wait. It will tell you whether, the reason pthread condition wait return, is it because the mutex because you have successfully waited for the mutex, or is it because the timer has expired? Okay, if the timer has expired, then you want to unlock the mutex and return. Otherwise, you can go back over here and reevaluate the guard. All right? Okay, so make sure you check the return code for pthread condition time wait. Okay, and again, one of the reasons you want to use pthread condition time wait is that this is an atomic operation. Okay, pthread condition wait without the time, right? It's an atomic operation to to unlock the mutex and get on the condition variable queue. Okay, so this function, it does three things now. It unlocks the mutex, wait for the condition by getting on the condition variable queue, and wait for the timeout simultaneously. Okay, so in this case, when you return, you will know that either you have that you have seen the condition, and because of these spontaneous return, maybe you haven't really seen the condition. It can also, the other possibility is that the timer has expired. All right. Anyways, check the return code. Okay. So that sort of finish thread safety. The next thing we're going to look at is deviation. Right? Deviation is that your thread is doing a single thread of execution, execute a bunch of machine instructions in sequence, and now it needs to do something else. Why would it need to do something else? Right? One is that you can ask another thread to deviate from its normal execution path. Okay, so something happened, and then you want your thread to do something else, right? So, for example, you are doing your warm-up number one, and somehow your program goes into an infinite loop, right? And then you press Control-C. Okay, when you press Control-C, well, we mentioned something called a signal that will sort of kill your process. Okay, so it sort of deviates from what it was doing before. Right? So that can be done using this thing called the unit signal mechanism. So actually what you can do is that in your code, you can actually specify a signal handler. So when I press Control-C, that particular signal handler is invoked, and your process is not getting killed. Okay, so basically you have this thing called don't kill me. So when somebody press Control-C, you will actually survive the Control-C. So instead of, your process getting killed, and instead of, staying in the infinite loop, your program will go do something else and then come back to the infinite loop. All right? So this is called, the deviation. And also, if you want to kill another thread, POSIX use something called cancellation. Okay? So if you have a bunch of threads that's running, okay, this thread can cancel the other thread, basically killing that thread without killing the entire process. Okay? If you want to kill the entire process, you can call exit. It's not very nice because some people might be doing something very important. So maybe one thing that you want to do is that you want to make sure that all the other threads get canceled. Okay? In warm-up number 2, one thing that you have to do is that you have to run 3 threads. One is called the arrival thread, the other one is called the token depositing thread, and the other one is called the server thread. Okay? They are supposed to run a simulation. The simulation will go on for days. Okay? So if the user get impatient, press Control-C. What you want to do is you want to gracefully terminate your simulation. So in that case, what you need to do is that you actually need to use both mechanisms. Okay? You're going to provide a way so that when Control-C is pressed, you're going to execute this function. Okay? This is a handler. Okay? When Control-C is pressed, you want to call this handler, and this handler is actually going to cancel all these threads because, the user says, I don't want to wait for this simulation to finish anymore. Finish now, whatever you have, report what you have done, and then, kill the process. All right? So we're going to look at ways to sort of do this properly by using the Unix cancellation mechanism. All right? And also be able to handle the Control-C, you're going to use the signal mechanism. All right? So first we're going to talk about signals, and then we're going to talk about pthread cancellation. All right, the original intent of unit signal is to force the graceful termination of a process, right? So over here, when we have, y divided by 16, y is equal to 16 divided by x, and x just happened to be equal to 0, it's a divide by 0 error, okay? So you might be computing for days, for some reason you end up with a divide by 0, okay? So what you're trying to avoid is to waste all that work. Okay, so Unix try to provide a mechanism so that when you get a divide by 0 error, you actually have a chance to save all your work before your thread is getting killed. Okay, so what happens is that you can specify a handler Okay? This handler is to be invoked when divide by 0 signal is received. Okay? So when you get a divide by 0, you will be able to invoke this signal handler to save all the current state. Okay? And then you can have a graceful termination of your program. Okay? Because if you don't have a handler, then all the computation will get lost because the operating system will just kill your process. All right? The second one is that, that if you're doing something, maybe you want an alarm clock to wake you up. Okay? So the alarm clock is going to come in as a form of a signal again. So you have a handler for your alarm. Okay? You say that when the alarm goes off, call this function. Okay? So this function might do something, maybe write out some of the important information, and then it will return so you can keep trying again. Okay? So normally, if you don't have if you don't specify a handler, when the alarm goes off, by default, you're going to kill your user process. All right? So this is a way to do something else when these things happen. All right. Somebody will actually call a signal a software interrupt. Okay? So it's really not a software interrupt. It's a callback mechanism, as we talked about, chapter 1. Okay? That it's a callback mechanism. You tell the operating system to say that when this thing happened, right, what is this thing? This thing could be divide by 0, could be the alarm going off. Do not kill my user process, but, do an up call and call my function instead. Okay? So here is your, let's say here's your thread. Okay? It's executing, in the address space, right? And now it gets a signal. Okay, so for example, if you do a divide by 0, you're executing the code right here. Okay, you have a divide by 0, so your user process or thread is suspended. You go into the kernel says, oh, you have specified signal handler, so I'm going to call that. I'm not going to kill your process. Okay, so it's going to make an up call. When it makes an up call, is your user thread still running? Okay, so that's kind of a weird thing, right? Because your thread is doing its normal execution, and the execution, well, they end up calling divide by 0. Okay? If you continue from that thread, what's the meaning of continue from that thread? All right? You got to make sure that you handle this kind of error condition. Okay? So you will provide a signal handler to say, when I have a divide by 0, call this function, and this function, inside this function, my thread, instead of executing this code, will go and execute the signal handler. So where is the signal handler code? Well, the signal handler code is in the other part of the code segment, right? It's your function, okay? So your thread is actually is going to be suspended from its normal execution. It's going to go execute that particular code, maybe set some global variable, because now it's still your thread executing, so it has access to all the global variable, all the heap, all the stack, and it can go do something. Okay? When it's finished doing something, it will return back to your normal condition. Okay? So this divide by 0, it will execute as if there's no problem, but then you should check whether your signal handler did something special so that you know that, that operation was not done correctly, so therefore I have to do something different. All right? So again, it's up to your code. The operating system provides this mechanism so that you can do something like this. Okay? All right. And the reason sort of people will call it a software interrupt is because it is possible, let's say if you're running multiple threads, you have a stack for one thread, another stack for another thread. You're running multiple threads, one's running here, the other one running here. You can actually have one thread send a signal to another thread. Okay? And therefore, this thread will interrupt what it's doing because it needs to invoke its handler. Okay? So that's why people sort of call it an interrupt. Okay? But please understand that if you don't do that, then signal is just an up-call mechanism. It's really not a software interrupt. All right? Okay? So it can be generated by the operating system in response to exceptions, divide by 0, take a square root of a negative number, things like that, accessing memory location that you're not supposed to. Or it could be caused by an external event, such as timer expiration, certain keystroke like Control-C, okay? Action or other process such as terminate or pause the process. So this could be another process, so another thread trying to deliver a signal to one of your threads, or Unix actually provide a mechanism for another process, so there could be another process that's somewhere else trying to interrupt what you're doing over here. Okay, so that's why, again, people call it a software interrupt. Okay, so this guy will be able to deliver a signal to your process. But again, delivering signal meaning that this guy make a system call inside the system, it says, oh, this particular signal needs to be delivered to another process, and this process has an upcall mechanism set up in case that this signal should be received. All right? You can also do user-defined events. You can actually have special signal to say that there's some special signal called sig user 1 and sig user 2. Those things can be user-defined, and then you can actually have one process send a sig user 1 event to another process. Okay, so only the application know what that means. Right? The effect on the process is termination. Okay, if you don't have a handler set up for a particular signal, your process will have some default action. If you have a handler set up for it, this handler will be invoked. Okay, and the default action will not be taken. Okay, and in that case, your process that's receiving a signal will be suspended. Or if your process has multiple threads, the thread that's executing, that thread will be suspended. Okay, and in order for that thread to invoke the handler, and eventually when the handler is done, it needs to resume the execution of that, or whatever it was doing before. All right. A few important terminology that are associated with the signal. Okay, the horizontal axis is time over here. There is a time where the signal is generated. For example, when you press Control-C, that's the time of signal generation. Where the timer expires, it's a signal generation. When you divide by 0, that's signal generation. Okay? As it turns out that the signal can, you can actually block a signal. So basically your process or your thread is declaring that right now is not a good time to interrupt me, okay, because I'm doing something important. So I can actually block a signal. Okay, so over here I can block a signal. Okay, so during this time when the signal is generated, this thread or this process might be blocking the signal. Okay, at some point the signal will become unblocked. Okay, I can say at this point I'm ready to receive signal. I'm going to unblock the signal. So if any signal that are waiting, a signal that's waiting over here is called signal pending. Okay, so this is similar to the interrupt terminology, right? And then when I say that, you can actually disable the interrupt. So when the interrupt comes, the interrupt becomes pending, and eventually when you enable the interrupt is delivered. Okay, so the terminology over here is exactly the same. Okay, if I have the signal blocked over here, then the signal becomes pending if it's generated while the signal is being blocked. Eventually, when the signal becomes unblocked, then a little bit later, right, it always takes some time, then the signal is going to be delivered to this user thread or process, and that thread will continue to execute. Okay, so there's a time of signal generation, signal getting unblocked, and then signal delivered. Okay? Okay, and we're going to use the terminology to say that the signal is pending when it's generated, but it's being blocked. Okay, when the signal becomes unblocked, it can be delivered. Okay, and if we replace the word signal by interrupt in this picture, the picture will look exactly the same. Okay, we're going to say that here is the sort of interrupt can be unblocked, and the interrupt can be blocked, and we have interrupt generation. The interrupt becomes pending until the interrupt is unblocked or enabled. Then we have interrupt getting delivered to the operating system. All right. Okay, so these are all the Unix signals. Okay, there's a long list. Okay, when you set up an alarm clock, when the alarm expires, it's going to generate something called sig alarm. All these things are integers. When you have a child process that died, you get a signal also. This is death of a child. When you get a floating point exception, when you divide by 0, taking a square root of a negative number, you're going to get signal FPE, floating point exception. If you are, connect to a terminal and then you're getting disconnected, you're going to get a hang up signal. If you execute an illegal instruction, you're going to get this signal. If you have a keyboard interrupt on the keyboard, you're going to get a SIG-in. All right, so when you press Control-C, SIG-in is going to get delivered to your user process. So again, this is why people call it software interrupt, because the SIG-in means interrupt. Okay, so unfortunately, it means hardware interrupt, and we're using the up-call mechanism. SIG-kill is another process trying to kill your process, and SIG-pipe is related to networking, quit, and then segmentation fault, SIG-seg-v. Process termination, somebody tried to stop you. So the stop and continue, these are used for suspending a process. Okay, so you can actually, have one process tell the other process to suspend, and then when it returns later. Okay, so if you're using Ubuntu Linux, right, if you're running a program, you can actually see that if you press Control-Z, it will suspend your process, and later on you can resume it. And that's by sending these kind of signal to your process. Okay, so over here, it explains what these signals are, and then these are the default action. So it means that if you do not provide a handler, these are the default action. Okay, term meaning that it will terminate your process. So it's not terminating the thread, it will actually kill your entire process. Okay, it says core over here is that when it terminates your process, it will actually generate a core dump. A core dump is that, it's going to take your process, take the entire address space, and write it to a file. Okay, and this file, by default, is going to be named as a file called core. You might have noticed that on your Nunkit account, you're going to have these kind of core file running around when you have, segmentation fault. Okay, so these signals, if you receive that, it will cause you to dump core. Okay, ignore meaning that nothing will happen by default. Okay, so if you don't specify a handler for sick child, if your child process die, then your parent will not notice it. Okay, because by default, it's ignored. Okay, if you call, so again, term, core, blah, blah, blah. Over here, there's a forced term. Okay, forced term is going to cause you a forced termination. So these signals, so there are actually two will cause forced term. That's sig kill and sig stop. Okay, there's no way for you to set up a handler for sig kill and sig stop. So if somebody try to kill your process will die. There's no way to stop them from doing that. Okay, more term and core and something like that. And then the suspend, it will cause your process to stop or suspend it. And then eventually when you call continuation, it will cause your process to continue executing. All right. The last two, the one I mentioned is sig user 1 and user 2. You can define it to be used inside your program for whatever, need that you have. All right. To send a signal to a process, you need the process ID of that signal, of that process. Okay, and you specify what signal you want to send. So you can say, I want to send sig kill. Okay, so this will deliver, to this process a signal, the kill signal. Okay, there are other ways to have signal generated. For example, you type Control-C, you're going to generate a sig in to the current running process. You can also use a kill shell command. You say kill -2, something like that. So this is the process ID. Okay, you're going to find out the process ID, and then you can send it the to signal. Okay. On Nunkey, 2 is exactly sig in, right? All these signals are just integers. So this one is the same thing as pressing Control-C on this particular process. Okay? You can also send a signal to a particular thread, and in that case, you will use pthread kill. So pthread kill, you need a thread ID, and then you send a particular signal. Okay? So over here, we're going to sort of worry about that. If you have a process running multiple threads, then when you send a signal, who gets it? Okay, I think that's in a few slides down. All right, handling a signal. Each signal in a process have at most one handler. Okay, so if you have multiple threads, they all have to share the same handler. Okay, to specify a signal handler for a process. Okay, so therefore again, this is a per process concept. Okay, so the function that you can use is either sig set or signal. Both of them are the same thing. Okay, these two functions, they will also return to you what is the current handler. Okay, and then there are some fancier functions they can use called sig action that specify some additional stuff. Okay, so the way that you can use this, you can call sig set or sig handler. Specify that for this, if you get this particular signal, call this handler. Okay, same thing. You can call signal. If you get this signal, call this handler. So this is called installing a signal handler for a particular signal. Okay, so you can call these things, and this one will return to you the old handler. So you can say sig, you can declare an old handler. And you say old handler equal to sig set, sig int, new handler. So what you're doing over here is to specify that this is going to be the new handler from this point on for sig in, and this one you're going to retrieve back what the previous handler is. Okay, so maybe at some point you want to use this to handle SIGIN, and later on you want to use the different things to handle SIGIN, and then you want to go back to the previous handler, so you can use this mechanism to do that. All right, there are some default handler, the one that I specify, so you can actually use the keyword sig_DFL to specify I want to use this the default handler. So you can call signal SIGIN. I want to use the default handler. You can specify right here. Okay. You can also say for this handler, when this happens, don't kill my process, just ignore it. Okay. Again, you call signal. You say SIGIN. I just want to ignore SIGIN. Okay. So when you do something like this, and when you have a runaway process, you try to keep Control-C your process. Your process will never die. Okay. So this might not be a good thing to do, but if you really want to do that, that's okay. You can actually ignore Control-C. All right, here's an example. I'm going to specify a signal handler. Okay, so this signal handler, the handler has to have the data type that returns nothing, and it takes one integer which tells you which signal that it has received. So this one basically says that one signal handler can actually be the handler for multiple signals. Okay, so when you come in here, you should check which signal take you to this handler. All right, so we're going to define this, declare the signal handler this way. And then we're going to say sigset SIGIN handler. So when SIGIN getting delivered by the operating system, please call this handler. All right? So in this case, when you run your code like this, you go into an infinite loop. What's going to happen is that this process will never die, right? Because if you run this program, if you keep pressing Control-C, you're going to see the handler is going to get invoked. You're going to keep seeing this message getting printed over and over again. It says, I have received signal number 2, whoopee. And you can't kill it. Okay, so the way that you can kill this process is actually you can use, you find out what process ID it is, you can say kill -15, and then with the process ID. Right, so this way, this handler is not used for signal 15, so therefore you can actually kill it. You can also say kill -9, okay, I think -9 is SIGKILL, okay, this is the signal that cannot be caught, so therefore it will always kill your process. All right? Okay, SIG action is a little complicated. You can use it in warm-up 2 or you don't have to use it. Because in warm-up 2, when you run your simulation, you've got to catch Control-C, so you have to use signals. Okay? What it does is that it allows you to specify additional signal specified by one of these arguments over here when the handler is called. Okay? Anyways, I'm not really going to go too much into it. All right. To understand the way that signal is being taken care of in your process, we're going to understand something called a signal mask. A signal mask, it's a set of, so signal mask is also known as a SIG set or a set of signals. So a set of signals is represented as a set of bits, right? We only have a limited number of signals, so they actually fit into a 32-bit integer. Okay? So we can declare a data type called the SIG set T over here. This is just a 32-bit integer. We're going to use every bit to represent one of the signals. Okay? So this is basically a bit pattern. So you've got a bunch of 1100, 11110, something like that. Okay? So this can be, some people will call it a signal mask. Some people call it a signal set. So the idea over here is that if the mask bit is set, if this bit, right, so let's say that this is index 0, 1, 2, 3, 4, and SIGIN is, signal number 2. Right? So therefore, this thing over here, if it has a 0, that means that that signal is not blocked. Okay? If it's equal to 1, that means that that signal is blocked. Okay? So the signal mask is actually stored for every thread. They have a different signal mask, and the signal mask is stored inside the thread control block. Okay? And the signal mask is actually what you need to check when you receive a signal. Okay? If a mask bit is equal to 1, the corresponding signal is blocked. So this one says signal 0 is blocked, signal 1 is blocked, signal 2 is enabled, signal 3 is enabled, 4 is blocked, 5 is blocked, etc. Okay? But it really depends on how you use the mask. Sometimes, you can actually use the SIG set, and you can actually use these bits in the reverse meaning. Okay? So please make sure you read the man page to see how exactly a SIG set is being used. Okay? But when SIG set go into the signal mask inside the thread control block, then the definition becomes this definition. If the mask bit is equal to 1, the corresponding signal is blocked. Otherwise, it's unblocked. Okay? So if you, so there are actually a bunch of functions that allow you to manipulate the signal mask. For example, you can clear a particular bit by calling, so to clear the entire set, you can call sig empty set, and you pass the address of the set. So this will basically make the signal set empty set. That means that set everything to be 0. Okay, and then if you want to remove, you can actually add and remove a signal from a set. If you call sig add set, so this one will take the set and then add the signal to it, right? So if you have sig add set given a signal sig hub, I think sig hub is signal number 1, so you will turn this bit into 1. Okay, if you call sig add set sig in of the set, you will turn this bit into 1. Okay, similarly, you can also start with a mask that has all the 1 bits in them. You can call sig fill set. This one will set everything into 1. Okay, and then this one will say sig delete set, delete signal hub from the set. They will send this guy into 0. Delete sig in from the set. It will send this guy into 0. All right, and then you can use this thing to pass the signal mask around. Okay, well, once you have the signal set, you can use that to pass it around. Okay, so now when we want to wait for a particular signal, so this we can set up an alarm clock, you wind it up, and then you go wait for it. Okay, so the idea over here is that we're going to call this function. This function, what it will do is that it will put your thread to sleep for a certain amount, and when that when the timer expires, sig alarm is going to deliver to your thread, and this function, so this one will start off a timer. When the timer expires, sig alarm will be delivered to your process. Okay, and at that point, you know, what should happen? So what you can do is that you use this particular thread, you start off the alarm, you wind it up, and then you go wait for it. Okay, so the pause is a system call. What it does is that it will wait for, what does it wait for? It waits for any signal to be delivered. Okay, if you have any signal getting delivered, then pause will return, and then you continue to execute. Okay, so this code actually doesn't work, right? What it will do is that it will set up the, the interval over here. The interval is a time val. Okay, a time val is a data structure that has 2 parts. One corresponds to seconds, and the other one corresponds to microseconds. So this one says, I want to wait for 1,000 microseconds, right? The first guy is equal to 0. The second one is equal to 1,000 microseconds. So I want to sleep for 1 millisecond. Okay, so this function will return, will set the timer to expire in 1 millisecond. Okay, and then you call pause. All right, so this function will not work because what if the signal gets delivered right over here? Okay, you start the timer off, but for some reason your thread gets switched out. Something else happened. Maybe you should run another process. So many milliseconds has elapsed, and then you return to execute this particular thread. And at this point, the alarm has already been delivered. Okay, so therefore, when you call pause, you might end up pausing forever because no signal is going to get delivered again. Okay, so therefore, this code might not work. Right, so you have to sort of wait for this signal in the right way. Otherwise, you're going to end up with, so is this a deadlock? Yeah, it's kind of like a deadlock, right? It's not a live lock. You wait for something, and something can never occur because, you missed the timing, right? Okay, another example for improper code, right? That's related to interrupt. Related to signal, right? Is that over here? What you do is that you have something called a status update. So you want to write a program that might run for a very, very long time. And since it runs a very, very long time, you want to sort of know the current status of your thread. All right, so one thing that we can do is that we can set up a signal handler so whenever you press Control-C, it doesn't really kill the process. Okay, when you press Control-C, this program will print out a status message. Say I'm at, I'm 90% done, I'm 40% done, or something like that. Okay, so how do you do that, right? So over here, I can set up a signal handler by calling sig set sig in handler. So this is, my handler. Whenever I press Control-C, I want to, display the current state of my, long-running process. So there's a global variable over here called state. I'm going to take this as an argument. I'm going to call it display the status. Okay, so who is updating the state? Well, over here, I'm going to update the state right here. Okay, so this one set up a signal handler and then call this long-running procedure right over here. It's going to do this for a long time. It's going to update the state, put something in here, and then it's going to compute some more. Okay, and then when it finishes a phase of the computation, it's going to change the state by calling update state, and then compute some more, and compute some more, etc. Okay, so over here you can see the progress bar, moving forward as this code started to execute. Okay, so what's wrong with this code, right? What happened in this case is that the handler over here is not, it's not safe with respect to so the code over here is not safe with respect to the delivery of an asynchronous signal, right? The signal is asynchronous because the user can press Control-C anytime, and you have no control of it, okay? So therefore, it is possible you're in the middle of updating the state, and at this point, if the user press Control-C, you deviate from your normal execution, you go execute this thing, and then you might end up looking at corrupted data, okay? What if this state point to a linked list? In this code, you're updating the linked list, and you press Control-C, and over here, you're going to end up with a segmentation fault. Okay? So what we need to do is to make sure that you can only update this particular state when it's safe to do so. Okay? We're going to make your code asynchronous, async signal safe. All right. To make it safe, right, can we use the mutex, right? So over here we say, well, since we want to make sure that this is safe, we already know how to do it. We put a pthread mutex lock here, pthread mutex unlock. In the handler, we're going to do pthread mutex lock, and then we're going to do display, and we're going to do pthread mutex unlock. Okay? This code doesn't work because you only have one thread. All right? So what happens is that if this guy is, if the main code is calling update state, right, that means that it has the mutex lock. Now, if you press Control-C, Control-C is going to come in. This guy is going to try to call the pthread mutex lock. Okay? So this guy, even though it's the same thread, but, I don't really know it's the same thread, right? So over here, I'm actually going to call pthread mutex lock because I really can't do this without having the mutex lock. So you're writing code as if there are two threads when there's only one. Okay, so this code is not going to work because, if this guy has the mutex lock, over here you will come and try to lock the mutex, you end up locking forever. Okay, so this one you will never end up calling display because you end up with a deadlock situation. Okay, so this code doesn't really work. All right, so the way that we're going to do this is that we're actually going to, similar to disabling and enabling interrupt, right? Because signal is, it's kind of similar to a hardware interrupt. We have a way to block the signal. Okay? So we're going to use a function called sigprocmask. Okay? So sigprocmask, what it does is that it can actually be used to enable and disable the delivery of a particular signal. Okay? So over here, it takes three arguments. The first one is, how do you want to use it? You want to unblock it, you want to block it, or you just want to copy the signal mask into the thread control block. Okay? And the second one is the argument is a signal. And the third one, this one is actually a return value. You can actually return the old signal mask when you call sigprocmask. Okay? The how takes three different arguments. One is sigblock, the other one is sigunblock, the other one is sigmask. If you call sigblock, what happens is that the new mask for this particular thread is the union of the current mask and what's specified over here. Okay? So basically you're adding this set to the current set. Right? And the way that you add them is that you're going to OR together the current signal mask inside the thread control block with this guy. Right? So if what's inside the thread control block is 1100001111, okay? And this guy contains 1111011110. Okay? What you do is you OR these two things together. The output is going to be 11110, and everything else is 1. Okay, so if you call sigblock, then you will union them. Okay, if you call sigunblock, then it will unblock this. But it's sort of a better way to sort of explain this is that maybe we shouldn't consider this operation. Okay, we're gonna look at the signal that's being set over here, and when we say block, we're gonna also block those additional signals. Okay, so in this sig set corresponding to sig int. Okay, when you call sigblock, it will actually add int to be a block signal. It will set that to 1. Okay, if you call sigunblock, it will actually try to set this guy to go to 0 if you, use the right signal set. All right, and the last one is sigsetmask. It basically take this pattern and then copy into the thread control block and take the thread control block, what's in the thread control block, and then put it right in here. All right, so the way sig proc mask is going to work, we're going to see how it works, right, in this example. The first one is waiting for the signal, okay? So the idea over here is that, you're going to unblock the signal and then wait for it at the same time, okay? So over here, we want to make sure that the signal cannot be delivered until that you're waiting for it. Okay, so therefore what we can do is that we can block out the signal, right? So we start with an empty set, okay, and we're going to add sig alarm to it. Okay, so now this particular set, the only thing that are in there is sig alarm, okay, and then we say block sig alarm in addition to whatever you're blocking. Okay, so now we are blocking something, and then at this point sig alarm will be blocked. Okay, so at this time if sig alarm happen, then it's going to become pending until it's getting ready to be delivered. Okay, so at this point, we haven't even set up the timer yet, right? And that's the right time to block the signal. Because once you starting to set the timer, it might go off right away. Okay, so the set I timer is going to be called after you have blocked sig alarm. Okay, and that's the right way to do it. Okay, so once you do that, and then you need to wait for it. Okay, but when you wait for it, you can't really call pause because, if you're going to unblock it and call pause, well, that's two different operations. Then what if you get the signal delivered right between, then you're going to wait forever again. Okay? So therefore, you're going to have to do something atomically. So the way that you can do this is called sig suspend. If you call sig suspend, the idea over here is that we're going to unblock the signal and wait for it at the same time. Okay? So this one, we're going to fill this set with everything, set everyone, and we're going to delete sig alarm from it. Right? So now this pattern become 1, 1, 1, 1. I don't know where sig alarm is. One of them is going to be 0. Everything is going to be 1. All right? And then when I call sig suspend, I'm going to give this set to sig suspend. Right? So in this case, I will only wait for the signal while all the other signals are blocked. Okay? And then atomically, I'm going to wait for the signal. I'm going to unblock, I'm going to unblock the signal, okay, so that I can receive sig alarm and then wait for it atomically. Okay? So this way, if your signal getting delivered, it's either getting delivered before this or after this, okay, before this guy or after this particular function is called. If this particular function is called, then you will see the signal, and then this function will also return, okay, because it's finished waiting for it. All right? So in this case, what you will do is that you will come back over here, and at this point, the signal mask will be restored, and then you know that you have successfully waited for the signal. All right? And eventually, you can actually restore the old signal by using sig set mask with the O set, and the O set you obtain when you are calling sig proc mask for the first time. All right, so this is the proper way to wait for a signal. All right? What about this long-running code? Right? So the idea over here is that we're going to make sure that this function can never be invoked, okay, by blocking out the SIGINT. Okay? So when we are ready to do update state, we can do a sig block, and we're going to block out SIGINT, right? The set over here, the global variable, it's set to be SIGINT right over here, okay? And we're going to store the old signal mask in the local variable over here, okay? So right before we're going to update the state, we're going to disable the delivery of the signal right here, okay? And then we're going to update the state, maybe the linked list involved. And then when we're done, we're going to restore the O set back into the signal mask. Okay, so therefore enable the SIGINT again, and then we can do compute more. Okay, so this way we guarantee that this signal handler will never be called when you are updating the state because that signal is blocked. All right, again, look at this code carefully, because you might have to do something like this in warm-up number 2. All right, and I mentioned already what async signal safety is. All right, okay, so what happened is that over here it talks about a funny situation. When you have a system call that's in progress, and then at that point you are delivering a signal. So what happens, right? You call write, and now you're executing in the operating system, and the user press Control C. Okay, what happened to the write? To write, I guess over here this is, well, there are a few options. Okay, you can deal with the signal with a system call complete. When the system call return, at that point, the operating system will do the up call and deliver the signal. Okay, another approach is you can interrupt the system call, invoke the signal handler, deal with the signal, and then you resume the system call. Okay, well, what if you kill the process over here? Well, then that's really not a good way to go. Number 3 is interrupt the system call, deal with the signal, and return from the system call with an indication that something has happened. Okay, so over here, okay, thank you. All right, the system call, you're inside the operating system, the condition happened, the operating system is going to make an up call. So when the up call is finished, what happens is that the operating system actually going to force a return of the system call, and it will also make an indication that the system call didn't really complete. Okay, so in that case, what happens is that the system call is going to return to you with the error number, indicate that this particular system call was interrupted by a signal delivery. Okay, so it turns out that Unix basically decided that this is the best way to go. Okay, so this is a very generic way of dealing with a signal delivery during a system call. So all the system calls are done this way. Okay, so if you have a code that looks like this, okay, when I'm trying to read data, I'm going to make a system call, right? So maybe I'm reading a lot of data. Okay, maybe halfway through the reading, I'm gonna, user press Control C, something, some other user send me a signal or something like that. Read actually gonna return. Maybe the buffer is gonna be partially full or something like that. Okay, but what the operating system needs to make sure is that the read, the file cursor hasn't been moved. Okay, when the file cursor is actually moved, that means that you have finished reading the entire block specified by the reader, and then all these data is gonna have valid data. Okay, so in that case, as a user, as a programmer, what you need to do is that when read returns, you should check the return code to see if it's equal to -1. -1 meaning looking at the error number, right? You look at the error number is going to say if error number equal to EINTR, that means that this system call was interrupted by a signal. Okay, so if you're writing a program that you expect signals, then every read you have to write it this way, because the signal can be delivered. Okay, so if error number equal to EINTR, what are you supposed to do? Well, that means that the read didn't really complete, or maybe it's somehow in a halfway finish. If you continue, you go back over here, you're going to read it again. Okay, so when you continue to read, well, in the operating system, you got to make sure that the cursor position hasn't changed. So basically, you perform a read request one more time while the cursor position is exactly the same place, and then you will start to read again to fill out that buffer with that much data. Okay? If the error number, is not equal to INTR, then maybe you're okay. Okay? In this case, it says the error is more serious because read return -1, and normally it's not supposed to do that. Okay? So therefore, maybe you will print an error and then exit. Okay? You will use P error so that print the right error message. All right. I only have 2 minutes left. So over here, it says that, well, when you do write, you also need to be careful. Okay? When you write to files, then it's a little bit tricky. If you want to write, let's say 10,000 bytes, okay, the file system sort of write your data in chunks. So maybe at that point, you finished writing several bytes, okay, and then you need to write again. But in this case, you shouldn't write at the same cursor position. You need to write a little bit further down. Okay, so part of your buffer might be written to the disk already, so you need to write the rest of it. Okay, so over here, this one shows you code that you need to use in order for you to write properly. Okay, and again, when you have signals, you got to have messier code to deal with writes. Inside the signal handler, we said that you should not use pthread mutex unlock. Pthread mutex lock. So what are the routines that are safe to be used inside the signal handler? Okay, so this is actually a complete list of all the functions that you can use inside the signal handler. But in general, you should only do as little as possible inside the signal handler and get out of the signal handler as much as possible. So usually what you will do, you set a global variable to say that, hey, a signal has happened, and you got to write your code so that when when your code make a system call, when it return, it will check this global variable to say, a signal has occurred, so therefore maybe I need to do something different. All right, so warm-up number 2, make sure you keep that in mind. All right, I guess I'm out of time. So Monday lecture, I will continue from this point on. All right?
concludes CS402 for Thursday, June 5th, 2014.